Here we have a sample problem. If 15 grams of calcium carbonate is produced when 60 milliliters of sodium carbonate is added to excess calcium nitrate, what is the concentration of the sodium carbonate? So this is going to work out the same way that it always does. What we see here is that we have a reaction between calcium carbonate, we have a reaction between sodium carbonate and calcium nitrate. And this is going to produce calcium carbonate. The other compound is not listed, but we can see it's implied. If calcium carbonate is one of the products, the other product is going to be sodium nitrate. So do be very careful that you don't do what I did automatically off the top and start with thinking, okay, the first chemical that's given here has to be a product. It's actually the second and the third chemicals that are the product. It's the sodium carbonate and the calcium nitrate. And I can figure out what the other chemicals are because I recognize, hey, both of these are ionic compounds. This is probably a double replacement reaction. Once I have a chemical reaction and it is balanced, next thing that we're going to have to do is write down our knowns. We know the mass of calcium carbonate being produced, 15 grams. We can also calculate the molar mass of the calcium carbonate as well. It's going to be 109 hundredths of a gram per mole. Then we write down our unknowns. We want to know what concentration is for this, and note, we're looking for moles per liter this time, which we wouldn't usually do with gravimetric stoichiometry. We rarely would end up looking for grams per mole because we can calculate that, but concentration we can solve for. So we're looking for concentration on the end, so I've put concentration on the top so that if I draw an arrow tracing my path, I end up with the concentration as the final thing I run into. And then of course I need the ratio as well. It's a nice clean 1-to-1 ratio here. So what I'm going to do is I'm going to start with my molar mass, I'm going to start with my mass, then I'm going to use my molar mass, my ratio, and finally I'm going to use my volume. So we're drawing an arrow across going over this way. So first thing, molar mass, 15 grams of calcium carbonate. Make sure you write down the chemical's formula in your calculations. It's part of the units too. I'm going to flip my molar mass upside down so I get grams on the bottom, moles on the top. Then I'm going to cancel out CaCO3. So I put CaCO3 on the bottom, Na2CO3 on the top. And finally, I have moles, but I want liters on the bottom. So now that I have liters in my Na2CO3 side, I'm going to put my liters at the bottom. If I plug that all in, that gives me 2.5 moles per liter of sodium carbonate. And it's to 3 significant digits because our smallest numbers were both 3 significant digits. Also remember as well, even though this was given in milliliters, I converted it to liters in here. Because what we really don't want is we don't want moles per milliliters. It's not terrible. Mathematically, it can make sense, but just in terms of the standards that we use, we could do millimoles per liter, but we would never do moles per milliliter. Here's another sample problem. What mass of potassium hydroxide is required to completely neutralize a 3.5 liter solution of hydrobromic acid with a pH of 2.5? And it has a lot of numbers after it or a lot of zeros, so that this will be to 3 significant digits in the end. Because remember, pHs are logarithms, so we only count significant digits after the decimal place. Okay, so a neutralization reaction is a reaction where you have an acid and a base reacting to produce a salt and water. So we need just enough potassium hydroxide to completely neutralize all of the acid. Now, with this question, we're not given a concentration or a volume, really, but what we are being told is that we are being told that the pH is 2.5. So we can calculate the concentration 2.5. We know that the formula for hydronium ion concentration is 10 to the power of negative pH. So 10 to the power of negative 2.5 gives us 3 16 times 10 to the negative 3 moles per liter. Now, the nice thing about this is we're dealing with hydrobromic acid, which is hydrogen bromide as an ionic compound. And the concentration of the hydrobromic acid, because it's a strong acid, is equal to the concentration of the hydronium ions. In Chemistry 30, you will deal with scenarios with weak acids where they're no longer equal to each other. But in this case, we can just assume that they are equal. So that tells us now we are given a volume and we have a concentration. That tells us that the concentration is 3.16 times 10 to the negative 3 moles per liter. Our volume is 3.5 liters of HBr. We have a 1-to-1 ratio in this reaction. We can calculate potassium hydroxide's molar mass at 56 11/100ths of a gram per mole, and we want the number of grams of potassium hydroxide in the end. And from here, this is just like any other stoichiometry problem. We're going to start out with 3.5 liters of hydrobromic acid. We're going to cancel the liters in the molar mass with the liters in the concentration with the liters in the volume. And unlike molar mass here, which is why I said its name because I was thinking about it, unlike molar mass, we don't have to flip this concentration because the liters already cancel out. It's not like molar mass having to flip so that the grams are on the bottom and they cancel with the grams on the top. This time liters are already on the bottom, so we just multiply them together. 1-to-1 ratio doesn't really change the math, but you still have to write it in to show your unit canceling. And then all we have to do is cancel out moles on the bottom so that we're left with grams on top, and we see that it takes a bit over 1/6 of a gram of potassium hydroxide, 0.621 grams of potassium hydroxide to cancel out a 3.5 liter solution of hydrobromic acid with a pH of 2.5. Even though it's very acidic, remember that potassium hydroxide is a strong base, so it is also very basic, so a little bit goes a very long way.